Thank you for coming. It's almost lunch, so we're probably hungry. Just want you to know, this talk is very important to me for two main reasons. First of all, my son is here today. Okay, my son is 14. He's actually a CEO. He's earning more money than I do. And I hope that next year he'll open a booth here at the conference. The second reason is that in 2005, a group of people told me that in order to build a neural network, you must know very complex math. And the second group in 2014, when I left Matlab for JavaScript, they told me, why are you leaving the grown-up language, Matlab, to children language, JavaScript? Okay, so let's hear a boo for these people, because you're all JavaScript developers. But seriously, this is going to be in-your-face talk, okay? Because we're going to learn how to build neural networks with third-grade math and JavaScript. Cool? And in the end, you'll need to help me to raise this in-your-face meter. Cool, so let's start by looking at neural networks. Neural networks, I think anyone who ever heard a talk about neural networks knows that neural networks mimic nature, mimic our neurons, which are the thinking cells in our body, or learning cells in our body. And this is an image of a barn owl hunting a mouse. It's not a real one, okay, because they work in the dark. But I used to research barn owls, their brain, and more specifically, their auditory and visual system. Okay, and actually, I researched neural networks in their brains. And how do you do that? Okay, let's say I want to find what a visual neural network does in the brain. So I make sure the barn owl is fixated, or stare is fixated on this red cross here. And then I show a stimulus, okay, like a circle of light or something like that, and I measure how strong the network responds to it. Okay, it sends an electric signal. Then I show the same stimulus in a different location and measure it again. Okay, and I do it in various locations in space, and then I show it in a bar chart. And what we can see that in a certain location in space, the cell responded gave the strongest response. Okay, that means that this cell tells the brain there is something in this position in space. Okay, and of course, the brain interprets it from various networks and eventually builds the image. But this is kind of not the real way things work, right? We're in that more dynamic world and things are moving. If the barn owl wants to hunt a mouse that doesn't move, it's probably a doll or something. It's not edible. So in my experiments, I used dynamic sounds that move from, let's say, left to right. And what we see in this picture is the same cell responding to a moving stimulus. It moved from left to right, and we see that at the beginning there was almost no response at all. And then when we entered the area the cell usually responds the strongest, and then we go out and almost no response. That is expected. The interesting thing is this, that if we look at where the strongest response was in the static stimulus, we see that the center was here. That was the strongest response. But if we test the strongest response from a stimulus that moves right to left, we see that the response was a bit to the right. Okay, and the same thing, only on the opposite side, happens on the opposite motion. So what this means is that this network told the brain ahead of time that something is going to be where it thinks it's going to be, let's say, 100 milliseconds later. Okay? And this is called a prediction. Okay, it's all about prediction. So the idea of neural networks is that they learn something, and when they see new data, new input of kind of the same context, they predict something. In this case, we predict where the mouse is going to be in a few moments. Or if someone throws a ball at you, you want to have enough time to raise your hand to catch it. Okay? But we also predict the next word, okay? Or we predict the next sound. Cool, makes sense? And now it's getting more interesting because now we're talking about LLM. Who cares about living creatures, right? So the next step in evolution. But seriously, if we move back to JavaScript, I said no math, or no more than third grade math. So we have a class, neural network, and it has a method, predict. Okay, that's the main goal of the neural network, to predict something, the next step. And we're going to predict something that might be relevant to everyone. We're going to predict if a developer is front-end developer or back-end developer. Sorry for the bias in that picture. And how are we going to do that? We're going to have 3 tests that the developers are going to have. Okay, we have 1,000 developers. We know which one is back-end or front-end, and we give them tests. And of course, if someone is good at CSS, he's probably a front-end. If someone is better at cloud, he's probably back-end. JavaScript should be kind of equal between the two. And we'll give these results to a neural network, and it needs to identify which is which. So back to our biomimicry concept. So if you look at a living cell has dendrites, which are, let's say, the sensors. They accept the input from outside. We have the cell body, which is the computational unit. It gets all the input, sums it up, and decides what output to send out. And it also sends something back to fix the characteristics of the dendrites. And if we take it to software engineering, then we have our inputs here. These are an array of numbers. And we have our dendrites, which are also numbers. And if we just multiply each input in its dendrites value and sum it up in the cell body, or a computational unit, it decides what output to give out. Okay? It's pretty simple. So again, no math. Let's see how it looks like in JavaScript. So we have our weights. Weights are the dendrites. We have 3 because we have 3 tests, 3 test results per developer. So we just create an array of 3 weights and randomly initialize them. Now we have our predict function. We're going to implement it. It just gets the 3 numbers, an array of 3 test results. We know the pre-ordered. And now we calculate this sum. Okay, this sum is just to sum the weight times or multiply by the relevant input or test grade. And eventually, we decide if we want to activate, like send what output to send. Do we activate the neuron? In this case, our activation function just gets this sum and decide if we return front end. Let's say if it's bigger than 0, it returns front end. Less than 0, it returns -1. Sorry, it was a presentation from front end developers, so we're a little biased here. But imagine that -1 is better. Okay, so this is our prediction algorithm, and this is how neural networks predict. Okay, we get input, we multiply and sum, and decide if we want to do it. So what I'm going to do, I'm going to take 800 of our 1,000 developers. Remember, we have their test results, and we know if they're back-end or front-end. And let the system see if it's working. So I'm going to test the network, and it gets like 51% success, 21%. It's not something we can build startup with, right? It's not really worth it. So why isn't our network working? Okay, the problem is that our network is a baby we just gave a black belt to, okay? And we wanted it to win competitions. But in order to win competitions, it needs to learn something, right? It needs to actually be given examples and know what to respond according to them. And how do we learn best? We learn best when it hurts, okay? When we lose something. So we just need to build an algorithm, a learning algorithm, that every time the network makes a mistake, we punish it, and then it knows to correct its way. So again, in JavaScript, it looks like this. We have the learn function that accepts our grades and the label. If the developer whose test results these are is front-end or back-end. We make our prediction according to our current weights, and we calculate the error. Okay, the error is our loss function, which is just subtracting the prediction from the label. Okay, if they are the same, if we were right, the error is 0. If not, it has a value, and we can use this value to fix our weights. Okay, again, if the error is 0, we make no change. If we made an error, then we change the weights according to the error and the input size. Cool? You can ask questions, by the way, because it's going to get a bit more complicated. Cool. Okay, eventually we return the error. We're going to use it to supervise our network. This algorithm is called gradient descent. Anyone heard about gradient descent? Raise your hands. Great. Okay, cool. So a few of you heard. Gradient descent is actually an algorithm that essentially, I'm not going to, again, without math, essentially supposed to reduce the error with every iteration until we get to a certain level of error we can live with. And we'll soon see how we do that. So we have prediction, and we have a learning algorithm, but is it enough? Okay, because imagine that you get a new Node framework, and you build your first component or module with it, and then you say, okay, I'm an expert with this one, right? So this is not true, okay? You need to make some more, create more components, work with the framework a bit, learn a bit, make some mistakes, learn from them. So we need more training for a neuron. And actually training the neuron will get all of our test results with the labels and send them to our learn function. Okay? And remember that this one, the learn function, returns the error. So we sum the errors and actually create the average error of our training cycle. Okay? So we actually train everything on all the data set that we have. Let's say 800 out of our 1,000 results. Cool. Okay, so these are, sorry, I skipped this one. Okay, and now, again, sorry, let's go back here again. So, okay, so we built a whole app, a whole app with our framework, and now we're still not experts, right? We need to do a lot more. We need to build a few more apps, or upscale, or do anything more than just the tutorial, right? So for this, we need to train the network on this framework or on our data more than once. So this is the algorithm to just repeat the same training process over and over again until we decide we can call this network good or expert or whatever. How does it work? We just iterate over a certain number. Let's say a maximum number. We call it epochs. For epoch is just the cycle of training on all of the data set. And we use the trained neuron that we built before. We calculate the error. We get the error from it. And if the error is 0 after a training session, we say, OK, so now the network has 0 errors or on the training set, so it's ready to go to production. OK? Sometimes, I think actually most of the times, the error will not be 0. OK? But this pretty easy data set, it can be. And this line is kind of technical. We'll just show the error after every 100 iterations. So let's train our network. We'll just move here to the training. We'll reset the weights. Okay, so we see we have the 29%. And now let's train the network and see what happens. Okay, we see the error, and it doesn't go down. Okay, it remains the same. It goes down, goes up, but it never converges to 0. Let's test the networks. Yes, 71%. It's better than our original network. But again, 71%, I think we can build an algorithm, a regular algorithm, that is much better than that. Okay, so what just happened here? So we have our learning, but it's still unable to learn our data. Okay, and that's because what we saw, it doesn't converge to the error level that we wanted. We wanted 0 errors on this case. And the thing is that convergence happens when the network is powerful enough. Okay, we need more power. So the data on if someone in front end or back end is too hard for this network. That's why we need HR. Yeah. AI won't take the jobs of HR yet. And for this, we have something called bias. And bias is kind of like the knights from Monty Python, but this time the knights who say I all the time. Essentially, in JavaScript, is just adding a new weight that always accepts an input of 1. Okay? So we just add it to our sum, only we don't need to multiply it with the input because it just has an input of 1. As simple as that. And of course, we need also to update it in the learn. So it's a way just like any other, and we update it according to the error, and it just adds more power. And you don't have to believe me because we have a live example. So this is the exact same network. You see, we start with the same weights, and we get to the same success level. And now we're going to train it with the bias. And after 101 epochs, it succeeds to get to 0 error. And now we test it on new data that is never seen before, and we get to 98% success. Okay, so can we fire our HR now? Okay, so what does this bias do? Okay, so in the chart, we see like a red square that separates the front end from the back end. Okay, and this is a representation, the visual representation of our weights. So the weights kind of, you can visualize it as if the weights can move this only this way, like change the slope. And the bias also allows us to move it between, let's say, give it an up and down motion as well. Okay? It's oversimplification, but that's kind of it. It gives it more power to move between the data and separate them. Okay, so we have prediction, we have learning, and we have bias. So now we have a working neural network, right? But the thing is that if you heard, actually, just recently, NVIDIA's CEO said that we have 2 problems. Okay, one is that we don't have enough capacity to manufacture enough chips for everyone, and chips not the one that we eat, the NVIDIA chips, and that we don't have enough power. Okay, in his last conference, he actually initiated an emergency conference that they said, we need more power, we need more electricity. And why is that? Because training our AI takes a lot of power and computational power. Power. And if we manage to differentiate between front-end and back-end developers so easily, why do we need more power? Because, as I mentioned before with the Barnold, the world is not just 2 kinds of people. We can have noise. Can you think of a noise that can enter our... Exactly. That's the reason I want it. Okay? So I get this damn full stack that corrupt our data. And our network might be good enough. I'll just reset the weight. Yeah, we got to this. Our network might be good enough to accommodate this noise, but look what happens. You see? Okay, it did converge, but it took like 6 times more than the filtered data that had only the 2 groups. So yeah, we might actually differentiate between people who are full stack but stronger with backend and full stack who are stronger at front end, but it takes much more time to train it, and we want to optimize that. So I'm going to explain of a way to optimize the learning, but it might be a bit counterintuitive, so bear with me. Our weights, we can look at them as coordinates in hilly terrain, where we start from some hill here or whatever, and we want to find the perfect spot in one of the valleys where it's shady and we can have a picnic. Okay? So if we change the weights in big steps, we probably jump from one hill to the other, and eventually we might accidentally fall in a valley, but it's most likely we'll just jump will teleport between these hills. Okay, or as we experienced as kids with this game, we might actually miss the sweet spot, or the one that we really want to hurt. But the thing is that if we do it in smaller steps, more delicate steps, we'll get to the result much faster. We'll get to a closer place to have our picnic in these hills. And the way we do that is by changing our learning algorithm and add another parameter to our network, which is a learning rate, okay? Which is a number between 0 and 1. And that means that every step, because we multiply our update, our weights update with it, so every update step is smaller, okay? More delicate. So it's like moving in smaller steps until we find the right spot. Okay, and let's see the effect. Sorry. Set that, and it's 29 again. And now we train with learning rate and finished with 19 epochs, even faster than our clean data. Let's test our network, and we got 92%. Okay, so we now have good prediction. We managed to make our network or neuron learn much faster, and actually upgraded its power using the bias. And what I did here was a pretty simple network, right? There is much more to tell. You can see this is just learning rate optimization techniques that you can learn, but if now you know what learning rate is now, so you can look it up. And there's also certain activation functions that fit every certain scenarios. Let's say you want to use images, or you want to create music with it, or categorize full stack and backend. So you'll use different activation functions. There's much more to learn, but these basics are the smallest Lego blocks of neural networks. And from here, you can just build bigger and bigger networks and play with the parameters, the activation functions, the learning rate. Okay, start with the bias, give the bias some frame of values it can use, and stuff like that. So we have this building block, but what about the big networks? Okay, I mentioned at the beginning LLMs and how they create music and predict the next word. And the thing is, again, that because we have this building block, you can now recognize that this thing is our small neuron. Okay, it has the bias, this is the input, and all the input gets in here. It has the computational unit, and it sends it to the next layer. Okay, so this is the input layer, and how does this layer is called? Anyone knows? Anyone? That's a hidden layer. Have you heard this notion? Okay, so we have our input layer, and in a network, all the layers between the output and the input layers are called hidden layers, and this is where the magic happens. Okay, this is where you get some very disassembled data. And every step of the way, we build the big picture. But also, the big network has the same concepts as the small neuron that we built. Okay, we get the input; it propagates forward in the same manner. Eventually, we have a prediction. We compare it to the true value. We get the loss function. The loss score is the error, and then we optimize it step by step. We just fix our weights to actually make a better prediction. And just like in Node.js, when you have a single service or even 2 or 3 services, it's not the same architecture problems as when you have like a microservice architecture with Kubernetes and stuff like that, and then you have lots of other problems with the load balancing. So it gets more complex. So here it also gets more complex in many ways. For instance, just imagine that you always multiply in a small learning rate. So the change can also be diminished. So if you multiply with something that's smaller than 1, and then again, and then again, and then again, then you get like 0.001, 0.0001, okay? And this is called vanishing, and exploding is the same, only we can get infinite weights eventually. And one last thing before you start implementing a neural network yourself, because it's very easy. As always, when we stand before a question, do we build our own or do we use an existing framework? Just know that neural networks has much more than that in technical specifications. For instance, using the GPU. Okay, it's not so easy to use the GPU when you make calculations, especially not in frameworks that run in the browser too, but I don't know if it's relevant for any of you. But just so you know, the building blocks that we learned here are used in the big frameworks. For instance, in Brain.js, you now know how to build it because you know that these are hidden layers. You have 3 hidden layers of 3 neurons each, and you can decide the learning rate. You can define the activation functions. We'll see it in TensorFlow. Now you do train, okay, the same way we did here, only we call the function a different name. And then you calculate the success when you compare here they call run and not predict, but you run the predict versus the label that you expect. So it's exactly the same with frameworks. And in TensorFlow as well, you create the layers. You can see you can define the activation function and how many units each layer. And you actually call it, instead of train, they call it fit. But it's using the same principles, the same building blocks. And now you can take one of these and play with them. Okay, so yeah, we talked about building blocks and, of course, architectural, consideration, how you architect a neuron, and architectural problems that might arise from extending it or combining several neurons together. I didn't stress it enough, but it is my impression, and I don't know if it's kind of a belief because I never checked it. But I think data preparation is the most problematic thing in neural networks because if you think about it, the data I showed you here is very simple. It's grades. It's already numbers. But how do you prepare music? Anyone uses Suno? Cool. How does it work? Do you know? Okay. Do you know that there is an alphabetic representation for music? That's how it works. It's great. It's amazing. But it's a totally different concept. But just think about it, that there is a neural network that is specialized in taking your prompt and seeing that it's jazz. So it's a neural network that specializes in creating the alphabetic representation of a jazz music. Okay? So it's pretty amazing. And they do it for all other types of musics. If you want to learn the math, by the way, this is a great website. I think they explained quite nicely, but just if you want to get into math, you don't have to. You can go straight to these libraries and play with them. Maybe create a survey at work and create a network that analyzes it and present it in a nice way in your next happy hour. You'll probably be the star of the event. And you can just play with it because what can go wrong, right, with playing with neural networks? We have 2 minutes, and I really need your help. So if you could answer this thing and help me raise the in-your-face level so people will know we can learn neural networks without math, and of course do it with JavaScript. I'll appreciate it. It was even built with neural networks, right? It's a Base 44 website. Pretty cool. I'm not affiliated with them. Yay! Oh no, who made a mistake? Uh-oh. Cool. So I actually built a neural network that's going to process your responses and see how good you are, and then we can send it to these people who told me JavaScript is children language. Oh my God, that's not good. Okay, let's go for it and see how did we do. 84%. I think we're good for the first lesson, right? Okay, so here's for you. You did very well. And thank you.